In this video, we are going to study about how other character representation methods work in the world, okay, with practical application. So first of all, we'll start with BCD. BCD is known as binary coded decimal. In binary coded decimal, we are focusing on representing only the decimal numbers from 0 to 9. Okay, so this is what we call binary coded decimal. What we do is we use a specific code for each digit in decimal number system so that we can use it in electronic items. Okay, for example, digital clocks. Okay, they work on this idea. So let's start with the codes. So we know there is a decimal digit. Okay, so it's like when converting from hexadecimal to binary or octal to binary, we had a table, right? Similarly, we also have for binary coded decimal digit and binary code. Okay, so we are coding decimal in binary, so that's why it's called a binary coded decimal. So we know in decimal we have 10 digits from 0 to 9. Let me write that down. Write them down: 7, 8, and 9. So if you remember when we studied about the hexadecimal to binary conversion, we used 4 bits, okay, because there are 16 digits. Okay, there are 16 digits in hexadecimal, which is equals to 2 to the power 4. So we used 4 bits, okay. But 10 is not a power of 2. Okay, 10 cannot be written down in the index form of base 2. Okay, so what we do is, since 8 lies between 8 and 16, okay, if we choose 3 bits, okay, if we choose 3 bits, that will not be enough to represent 10 digits, okay. But at the same time, if we choose 4 bits, there will be excess bits. So what do we do is, we assign 10, okay, 10 specific outputs or the 10 specific codes for decimal digits, and we discard 6 combinations. Okay, we remove 6 combinations. I mean, in 2 to the power 3, there are 8 combinations, so that is not enough. But 2 to the power 4 is 16 combinations. So what we do is, we assign 10 combinations for the 10 digits and we remove the excess 6 uh, combinations. So it happens like this. And when you are writing this, there is a pattern that you can follow. Since you're using 4 bits, what you can do is, first of all, the last bit, okay, we have 4 bits, right? We have 4 bits. In the last bit, what you can do is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Yeah, alternatively changing the bits. Okay. Then in the second bit from right, okay, what you can do is, you can write out 0, 0, 1, 1. Okay. Here you're changing one by one. Here you will change once 2 digits. Okay. So 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, and you can put 1, 1. It's not required here because we need only 10 combinations. Then we have 0, 0, 0, 0, 1, 1, 1, 1. Okay, here now we are alternating between 4 digits. Okay, 4 combinations. So 0, 0, 0, 0, 1, 1, 1, 1, and finally 0, 0. And similarly, you must have guessed it, here we should have 8 zeros and then 8 ones and 8 zeros and so on. So 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. Okay, so if you can write them down like this, okay, you can come up with the exact coding. So 0 is represented by 0, 0, 0, 0. Okay, 4 is represented by 0, 1, 0, 0, and 8 is represented by 1, 0, 0, 0, or even 6. Yeah, 6 is represented by 0, 1, 1, 0. So this is how you can write them down without actually memorizing anything. Okay, so this is how binary coded decimal works. So what are the discarded combinations? The discarded combinations will be 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and finally 1, 1, 1, 1, because these 6 are not required in decimal number system. Okay, so only we need 10 combinations. Perfect. Now what we are going to do is, we are going to do an example question. Okay, so let's say we have to represent 4328 to the base 10. Well, in binary coded decimal, you have to keep in mind, this is not binary. This is binary coded decimal. Okay, so binary coded decimal. So what is the code for 4? It will be 0100. And for 3, it will be 0011. And for 2, it will be 0010. And for 8, it will be 1000. So this is how you have to represent binary coded decimal. Can you put 2 here? No, because this is not binary number. This is binary coded decimal. This is a code. Okay, you can't put 2 here. Well, now let's say we have something like 69973 to the base 10. Well, what will it be? 6 is 6 can be given as 0110. 9 can be given as 1001. 9 is again, so 1001. 7 is 0111. And 3 is 0011. Okay, and let's do another question. Let's say we have 753688 to the base 10. Well, that will be 0111. 5 is 0101. 3 is 0011. 6 is 0110. 8 is 1000. And finally 1000. Keep this in mind. This is binary coded decimal. You can't neglect any zeros. Okay, you have to write down the zeros whether you like it or not. Okay, and now let's do a 9-digit number, something like 987324167 to the base 10. Well, 9 can be represented as 1001, 8 is 1000, and 7 is 0111, 3 is 0011, and 2 is 0010, 4 is 0100, and 1 is 0001, 6 is 0110, 7 is 011. Okay, so what are the important things that you have to keep in mind? In binary coded decimal, we use 4 bits to represent a single decimal digit. Okay, and most importantly, this is a code. It's not the exact conversion from decimal to binary. This is conversion from decimal to binary coded decimal. Okay, now let's talk about ASCII. Okay, ASCII. Okay, this is what we call ASCII. What is meant by ASCII? ASCII means American Standard Code for Information Interchange. Okay, ASCII is American Standard Code for Information Interchange. Okay, so we'll just call it ASCII. You don't have to memorize all this, abbreviation. So what does this do? Well, ASCII is used to represent characters, not only numbers. You can represent alphabets, uppercase alphabets, lowercase alphabets, even numbers 0 to 9, no issues. Okay, so the thing is, ASCII uses 7 bits. Okay, 7 bits to represent characters, which means 2 to the power 7 characters, which is equals to 128. 120 is not exactly enough to represent all the characters in the modern world, but this was not introduced in the modern world. Okay, because it was a long time ago. It was actually proposed by the American National Standard Institute, but nowadays it's not used exactly, but they were used in IBM personal computers. Okay, even though I say they are using 7 bits, okay, they actually take up 1 byte, which means they use 8 bits, and the 8th bit is for checking. Okay, so the 8th bit is called as the last bit, is called as the 7th bits plus 1 bit, and this last bit is for checking. Okay, they call it the check digit. Okay, check digit, whether the information is passed correctly. You check that using this check digit. Okay, so this is what the basic idea is. There is a table for this. That's a huge table. We can't remember 128, obviously, 128 characters. Capital A is represented as 65. Okay, 10000001. Okay, so capital A is represented as 10000001 in ASCII. What do I mean by 65? Well, if you convert this to decimal, it will be equals to 65. Okay, so that's why I said 65, because it will be easy for you to keep in mind. But yeah, the capital A is represented at 10000001. Okay, so from A to Z, it is in this order. So what I mean by this order, B will be equals to 1000 0, 1, 0. Okay, and C will be equals to 1, 0, 0, 0, 0, 1, 1. So since A is equals to 65, B is represented by 66, and C is represented by 67. So let me ask you a question. What do you think Z is represented by, the letter Z? Well, it will be 90. Why? Since 65 is represented by A, B is 66, C is 67. And if you add 25 to this, I know Z is 26 letter, but A is the 65th one. So from A to Z, you just have to add the 25. Why? This is the first letter. And if you add 25, you will get Z. Okay. So here also it's the same thing. You will get 90. Okay. So 90 means how can you represent? 64. There is no 32. There is 16. There is 8. There is no 4. There is 2. There is no 0. I mean, there is no 1. So it will be 64, 80, 88, and 90. Okay. So what are the questions that you can face? Okay, that you may face in ASCII? Well, they might say A is represented by decimal equivalent of 65 in ASCII. They will give you this. They will give you the table or they will give you this data. Okay. And then they will ask you to write the ASCII code for something like this. FACE, face. Okay. Write this down in ASCII. So what you have to do is, since A is 65, okay, A is 65, you have to find for F, C, and E. Okay, so what is F? F is the sixth letter. A, B, C, D, E, F, which means you have to add 5 to this. So it will be the 70th one. And C is third letter. Okay, so you have to add 2 to that. So it will be 67. And E is fifth letter. So it will be 69. Okay, and then you will write down the ASCII equivalent. So A can be given as 10000000 1, and 70 will be equals to 10000110, and 67 will be equals to 10000011, and 69 will be equals to 100001. Well, it won't be 011, it will be 101. Okay, so 64, 68, 69. Okay, now you can't write down in this order because the order is FAC. So first of all, you have to write down F. F is given by 10000110. A is given by 10000001. C is given by 10000011. Okay, and E is given by 10000101. Okay, so this is how you can represent characters by using ASCII. Okay, American Standard Code for Information Interchange. Okay, so let's say we have something like space. Well, not spike. Spike. Yeah, spike is better. There are different letters. Since A is 65, okay, let's go with in order. So A, B, C, D, E. E is the fifth letter. Okay, E is the fifth letter. And F, J, F, I, no, I am making a mistake. F, G, H, I. I is the ninth letter. Okay, I is the ninth letter. F is sixth. F, G, H, I, yeah, I is the ninth letter. J, K is the 11th letter. Okay, K is the 11th letter. L, M, N, K is the 11th letter. L, M, N, O, P. P is the 16th letter. Okay, P is the 16th letter. And Q, R, S. S is the 19th letter. S is the 19th letter. So what we can do is, since A is first letter and that is represented by 65th one, which means E should be represented by 70, no, 69. You have to add 4 only. Okay, and I is 9, you just have to add 8 to this. So if you add 8 to this, what will you get? 73. And similarly, here you will get 75, here you will get 80, and here you will get 83. That's all. Okay, so keep this in mind. Keep this in mind. Now what you have to do is you have to write down in the order that is given in the word spike. So first of all, you have to write down S. So what is S? It will be 64, no 32, 80, no 8, no 4, that is 2, that is 1. So you have to write down 10100111. Okay, and for P, it is 80. Okay, so what you have to do is 10100000. Okay, so it will be 10100000. Then we have 75. Okay, so which will be equals to 1 0. We can't have 16 also, so no 16. That can be 8. Okay, so it will be 72. then we need more 3, right? So it will be 1. So it will be 1 0 0 1 0 1 1. And for 73, it will be 64, 72, and 73. So 1 0 0 1. Wait. I'm making a mistake, aren't I? I should come first. Yeah, I should come first. I should come first. I have to write down I first. 1 0 0 1 0 0 1. And for K, we have already found that out. And for E, we have 1 0 0 0 1 0 1. How did I write that down directly? Because I found it here. That's it. So this is how you can convert from ASCII to, not ASCII, to characters to ASCII representation. Okay, so this is the second one. Then we have EBCDIC. Okay, extended binary coded decimal interchange code. Okay, so this is also used in IBM mainframe computers. It can they use 8 bits for the character representation. They use 8 bits for the character representation, which means 256 characters can be represented. Okay, it's not much, but obviously better than ASCII. Okay, and then we have Unicode. I'm not going to do questions in this also. I don't think you will have questions in that because ASCII is the most important one that you should focus on. EBCDIC, there is no much data, but if they give you a table and ask you to write down, do what I taught you in ASCII. Then we have Unicode. Unicode is a very important thing. Okay, Unicode is a very important thing. I think most of you watching this video must have heard about it. Okay, because they use 16 bits, a stunning 16 bits, which is 65,536 characters. Okay, so why do we need Unicode? Well, for starters, let's think about the characters that we know. Okay, not only in the keyboard, think about the emojis. Okay, think about the emojis. Well, emojis are also characters, right? So we need something to represent them also. And that's why we need Unicode. Okay, that's why we need Unicode. It's a 16-bit code. Okay, there are many characters. Not only English, we can also represent other languages. Sinhala, Tamil, German, any language. Okay, so that's why we need Unicode. Okay, so this is what you have to know. There are some advantages and disadvantages. Okay, I'll just share it with you and read it when you have free time. I'll attach it in the link, the Google link, Google Drive link for that. And yeah, that's it for the character representation using different systems. In the next video, I will be concluding this series also. We have to just look at some bitwise operations, and yeah, that's it. And that ends. I was thinking of starting logical gates for everyone. Yeah, stay tuned.
Thanks for watching the 19th video in our number system series. If you found this tutorial on character representation methods like BCD, ASCII, EBCDIC, and Unicode helpful, don't forget to like, share, and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos, check out the full playlist to master number systems, and follow us on Instagram. I'll see you in the next video. Until then, keep learning and stay curious. Bye-bye.